An atomic bomb and a nuclear power plant works on the same basic principle, nuclear fission chain reactions. But what exactly is this? And more importantly, if the same thing is happening inside both a bomb and a nuclear reactor, then why doesn't the nuclear reactor just explode like a bomb? What's the difference? Well, let's find out. So, what is nuclear fission? Well, the word fission means breaking. So, nuclear fission is a nuclear reaction in which a heavy nucleus breaks into smaller nuclei. But how does it break exactly? Well, one way is for it to break spontaneously. It can happen all by itself without us having to do anything. But we usually call that radioactivity, or we sometimes also call it spontaneous fission. But when we usually say nuclear fission, we're talking about the ones where we break it by specifically bombarding it with a neutron. Think about it. This nucleus is already unstable. Now, you add another neutron to it, it makes it more unstable, kind of like pushing it over the edge, and then it breaks into smaller nuclei. And here, when it breaks, you also end up getting a few neutrons. You get somewhere between 1 to 3 neutrons usually out. So let's take an example. If you take uranium-235, an isotope of uranium, and if you bombard it with a neutron, then it can break into strontium-94 and xenon-140. We don't have to remember the numbers or anything, don't worry about it. But my question would be, can we predict how many neutrons we'll get over here? Well, we can. All we have to do, just like any nuclear reaction, is to keep track of protons and neutrons. So if I keep track of protons, let's see, I have 92 protons on the left-hand side. How many protons do I have on the right-hand side? Well, 8 plus 4 is 2, so 12, 5 plus 3. Okay, I get 92 over here, okay? But what about the total number of particles? Well, I have 235 plus 1, that is 236 on the left-hand side. But over here, 94 plus 140, so I get 4. 9 plus 4 is 13, so 1 carryover, I get 234. So there are only 234 particles over here, which means 2 particles must have been released. And these must be 2 neutrons because we've already accounted for all the protons. So that's how I know that there must be 2 neutrons released over here. But you know what's cool about nuclear fission reactions? For the same reactants, you could get completely different products altogether. For example, if we take another uranium-235 and bombard it with another neutron, look, exactly the same reactants, but this time you might get completely different products. You might get barium-141 and say krypton-92. Again, we'll get some amount of neutrons. When you pause the video over here and try it yourself to figure out how many number of neutrons we should be getting here. All right, again, we can see the number of protons is balanced. You have 56 plus 36 is 92. But how many total particles we have? We have 236 here again. This time we have 1 plus 2, 3, 14 plus 9 is 23. So you get 233, which means, look, 3 particles are missing. So this time we'll get 3 neutrons. And just like with the fusion reactions, we will see even here some energy is released. And energy is released usually as kinetic energy of the products and the neutrons. And because energy is released, and remember that energy and mass are equivalent, we will find that the mass of the products will be smaller than the mass of the reactants. And just by figuring out the difference in the mass, you can figure out how much energy got released. That difference in the mass is basically what got released as energy. Again, something that we've seen before in the nuclear fusion reactions, very similar. Now, can any heavy nucleus give you fission reactions? No, that can't happen. The ones that do, we call them fissile nuclei. So uranium-235 is fissile because it does undergo fission reaction and gives you energy. But if you consider another isotope of uranium, which is say uranium-92-238, turns out it is non-fissile. It does not undergo nuclear fission easily. And if you're wondering why certain nuclei are fissile and others are not, well, it has something to do with energy and stability. Well, it turns out for uranium, when it undergoes fission, you end up getting more stable products and therefore energy is released. Turns out that's not the case for uranium-238, or at least that's not very easy to happen. But of course, we'll not dive too much into it. But a big question now we could ask ourselves is, how much energy do we get out of it? Well, if you look at a single reaction, of course, we'll get a tiny amount of energy. But if you want to get usable amount, then we will require lots and lots of reactions. But how do we do that practically? Because nuclear fission requires you to bombard a uranium nucleus with neutron. So how do we ensure we get lots and lots of reactions like this? Well, the answer is right in front of us. Since each nuclear fission reaction gives us a few neutrons, if we can ensure that these neutrons go and hit other uranium-235 nuclei, then they will again undergo fission and it'll give you more neutrons, which cause even more fission reaction. Here's the way we can show that. So let me just go to the next page. Here we go. So if you have one neutron that bombards with a uranium-235, giving you energy, fission reaction, giving you energy and some neutrons. Now, if these neutrons could go and hit even more of these uranium-235s, then you will get even more energy. And this thing can keep on going, and you can see very quickly this will keep increasing. You initially have 1 fission, then you have 3 fission, and then you'll have 9, and so on and so forth. So the amount of fission happening per second will just keep increasing. This is what we call a chain reaction. Nuclear chain reactions can be quite devastating. You start with very few reactions per second, but very quickly, very rapidly that number increases, and within a short amount of time, you can release tremendous amount of energy. That is the whole idea behind atomic bombs. What makes atomic bombs so much more devastating compared to traditional regular bombs is that we're dealing with nuclear energy, which is orders of magnitude higher than the chemical energy that we get from traditional bombs. So a small amount of fissile material can give you a lot of energy. But that's not it. That's not it. You see, the products of nuclear fission reactions are usually radioactive, which means even after the explosion is done, the whole area is contaminated with radioactive isotopes now, which can further cause damage for years to come, making that whole area inhabitable. So yeah, atomic bombs are really, really destructive. But on the flip side, if you're using this to generate electricity, let's say, then we'll get way more energy compared to what we get from fossil fuels, because again, there we're dealing with chemical energy. And of course, another advantage of using nuclear energy is that in fossil fuels, because you're using combustion reactions, there is CO2 that is released into the atmosphere. None of that happens over here. But now this brings us to the original question: how do we use chain reactions in nuclear power reactors to generate electricity? Wouldn't they just explode just like an atomic bomb? So what's the big difference? Well, the big difference is over here, when it comes to bombs, we're using uncontrolled chain reaction. Whatever we just saw right now, that's called uncontrolled chain reaction. But when it comes to nuclear reactors, we use controlled chain reactions. How do you control chain reactions, you ask? Well, one of the most common ways is by absorbing a lot of neutrons. So imagine we absorbed a lot of neutrons like this. Then look, by absorbing neutrons, you are controlling how many further fission reactions are happening. This way you can control it. You can ensure that the energy is released in a steady rate, and that's how you can get controlled chain reaction. But there's another major difference. Remember how we said earlier that uranium-238 is non-fissile? Well, it turns out if you take a uranium ore, then most of it is actually uranium-238. That means you cannot directly use a uranium ore either as a bomb or as a fuel for nuclear power plant. This means we have to take it through a process where we increase the amount of fissile material, and this process is called enrichment. And the big difference is if you're using, a fuel you're using it for a bomb, then we would want a lot of enrichment. In fact, we would want about 90% enriched. And that makes sense because you would want as many fission reactions happening as possible per second so that the whole thing explodes immediately. But when it comes to nuclear reactors, nuclear power plants, you see we have only about 3 to 5% enrichment. That means a single uranium-235 is surrounded by a lot of non-fissile materials. That's why the material inside, that's why the nuclear fuel will not explode like a bomb, because it's not enriched as much as you would need for a bomb. So anyways, by using controlled chain reaction, we get energy as the kinetic energy of these products, which is then used to heat up water. And then the process is very similar to how any other power plant works. The heated water produces high pressure steam that turns turbines, and that's how you eventually get electricity. And then that hot steam is cooled in a cooling tower, and in the process, a lot of water vapor is produced and that is released over here. I'm mentioning this because I used to think that this itself was a nuclear reactor and it was producing a lot of smoke, radioactive smoke, which could be dangerous because it's going into the atmosphere, but none of that. Because first of all, this is just a cooling tower, and what it is releasing is water vapor, and that water never comes in contact with any of the radioactive material that you have over here. So it's not dangerous. But there will be radioactive products, leftover radioactive waste inside the nuclear power plants, and that needs to be safely disposed. And that is a challenge that scientists and engineers are actively working on today.